Welcome back to Arxflix. Today, we're diving into the second part of our series on reinforcement learning from human feedback, RLHF, in large language models. This time, we're focusing on the crucial component of RLHF, reward modeling. Reward models are trained to act as proxies for human preferences, guiding the reinforcement learning process. But they face challenges like noisy preference data and poor generalization. This paper explores solutions to these issues. Let's start by understanding how noisy data affects reward model performance. This figure shows the distribution of preference differences calculated from 10 reward models. Notice the significant number of data points with mean preference differences close to 0, indicating weak preferences. This figure shows the mean and standard deviation of preference differences for different data groups. The U-shaped curve of the standard deviation suggests that data with strong preferences and significant errors are harder for different models to agree on. This figure shows the consistency between original annotations and GPT for annotations for data groups with varying preference differences. The higher the preference strength, the higher the consistency. This confirms that preference strength can be used to evaluate the correctness of preference annotations. The paper proposes methods to mitigate the impact of noisy data and fully leverage high-quality preference data. First, they introduce a preference strength measurement metric based on multi-reward model voting. This allows them to identify incorrect and ambiguous preferences. To address incorrect preferences, they propose label flipping, where the labels of incorrect preferences are reversed. For ambiguous preferences, they use label smoothing, which penalizes overconfident model outputs. Finally, they introduce an adaptive margin component to the loss function, which assigns larger margins to pairs with distinct responses and smaller margins to pairs with similar responses. This figure shows the performance of reward models trained on different data groups. The data with the lowest preference strength negatively impacts the model's performance, while data with strong preferences significantly improves it. This figure compares the performance of different reward modeling approaches on 3 validation sets. The proposed methods, including label flipping, adaptive margin, and soft labels, demonstrate better performance and mitigate overfitting. To improve the generalization ability of reward models, the paper explores contrastive learning. Contrastive learning helps the model learn unique features by comparing similar and dissimilar samples, leading to better generalization. The paper proposes 2 approaches for contrastive learning in reward modeling, using preference pairs and preference differences. They utilize SWAV and SIMPS, 2 popular contrastive learning methods, to enhance the reward model's ability to recognize subtle variations and similarities in the data. This figure shows the training curves for the reward model trained using contrastive learning and the baseline. The contrastive learning-based methods lead to more stable returns and rewards during PPO training. The paper introduces METARM, a method that aligns the original preference pairs with the shifted distribution through meta-learning. METARM aims to maximize the difference loss function, which measures the degree of difference in the scores given by the reward model for responses sampled from the shifted distribution. This meta-process helps the reward model learn more about the original preference pairs that provide more differentiation between responses sampled from the shifted distribution. This figure shows the experimental results on out-of-distribution data. The proposed method outperforms the baselines, demonstrating its ability to generalize to new domains without the need for extensive preference labeling. This figure shows the reward score difference distribution of METARM and the vanilla RM. The significant difference indicates the effectiveness of METARM in enhancing the reward model's discriminative power under a shifted distribution. This figure shows the training curves of METARM in different rounds and vanilla PPO. METARM demonstrates enhanced stability and effective exploration, achieving better rewards after experiencing the same magnitude of changes in the output space. This paper presents valuable insights into the challenges and solutions for reward modeling in RLHF. By addressing noisy data, enhancing generalization, and aligning with shifted distributions, The paper contributes to the development of more robust and effective RLHF systems. The research highlights the importance of data analysis, contrastive learning, and meta-learning in improving reward modeling. These techniques pave the way for more aligned and capable language models. Thanks for watching. Don't forget to like, subscribe, and share this video with your fellow AI enthusiasts. Stay tuned for more exciting research summaries from Arxflix. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.